Hello, this is Bruce Wallenberg. This is Lecture 10B, the Part 2 lecture on transmission system effects. We're going to talk first of all about another power flow formulation called the decoupled power flow. What the decoupled power flow does basically is decouple or separate the P theta relationship from the QV. It turns out that real power and phase angle are much more tightly related to each other than the other two, and the Q, or reactive power, and the voltage magnitude variations are tightly coupled. And you can actually separate them and solve them as separate parts of the problem. And what we'll see is that this results actually in a faster power flow, one that uses less storage, if that's a problem, but usually it isn't. But the speed, it does gain speed for us, partly because the Jacobian matrix is no longer has to be recalculated each iteration because it's constant. It changes only if the reactive limits on generators change. So let's start. We're going to simplify the Jacobian, and we're going to do so as shown here. We're going to neglect the interaction of P and voltage magnitude, and we're going to neglect Q and phase angle. So we let the cosine, we assume that the cosine I minus j is approximately 1. That's because the phase angles are small. So we can say that the cosine is approximately 1. And since this is small, assume that this is much less than B. B and G are the susceptance and of the line admittance, okay, the conductance and susceptance of the line admittance. And finally, we also we assume that the Q is much less than the B. This is the B on the diagonal term of the Y matrix times the VI squared. And when you do all of that, you end up with the dP d theta term is just equal to product of VI, VK, BIK, and the dQ DE, or this should really be V in here, is equal to VI, VK times the BIK. Now that's the QV equation. Now when we rework these equations by dividing P, the delta P divided by V at its bus and so forth, we get an equation here where this matrix is called B prime and is a constant matrix. And what it is it's the matrix where we ignore all of the susceptance, with the conductance terms, and it only uses the susceptance. Whereas the B double prime matrix relates the delta Q and the delta V's. Of course, we divide by this V term over here again. And this is the actual susceptance for each line in the network. So again, this B prime Ij is 1 over X Ij. Well, we're going to see later that this is also the same definition of what we call the linear or DC power flow. So the solution: you build the matrices, you build them out, and they're approximately n by n, and then you solve equation for the delta thetas. Now that's this equation here. You solve this by inverting this matrix. Then you go back and you update You take the delta thetas and you update and you get a new delta theta, recalculate the Q terms and get the new delta Qs, and then you go back and, pardon me, and you calculate the inverse of this and get the new delta V, and then you update that. This figure shows E in here, and it should be V's. So if it's not converged, you go back, and so we call this the P theta. I put a little dash in there. The P theta half of the iteration, and the other one is the QV, and that's typical, the P theta QV, P theta QV. There's no necessity of trying to do only one or the other, but this is the way, and it generally takes more iterations to solve than the Newton. The original Newton we often refer to as the full Newton, where you've got all the derivatives. This takes more iterations. Let's say the full Newton solved in 3 iterations. This might take 5 or 6, but they are much faster, so the overall time of the power flow is faster. Now, there's one more method that was actually the original method, developed back in the 1950s, when digital computers were definitely still vacuum tubes in those days. And the paper that I remember reading was a paper by 2 authors named Ward and Hale. And you take the complex equation for P and Q at bus K is VK times the total current. The total current is basically summing one row of the Y matrix times the column of voltage. These are all complex terms. You take the conjugate of this, and when you write this all out, if you write this all out, you can then solve for a new term of V sub A, and you do that by you write this all out, then you take the VA term out, and it comes out to be a term where we take this. Now, alpha is the iteration count. Alpha is the iteration count. And you take the P minus JQ divided by the old value of VA. And here we say we're going to go through and multiply VJ times YKJ for all the new values. For J less than K, and for J greater than K, they're the old values, Vj times Y. Now, what you do in the Gauss-Seidel is you update the voltage at one bus. So you would update the number 1 bus voltage. Then you would update the number 2 bus voltage. And the number 3. There's no matrices being built. So this one will operate very nicely on a very small amount of memory, which was useful in those days, and became the standard power flow for many years because they didn't have computers with hundreds of G bytes of memory or tens of G bytes of memory. They were lucky to have tens of kilobytes of memory. So this method didn't need a lot of memory, but you do bus 1, bus 2, all the way to the last. Let's say you're doing 500 bus power system. You'd get to the 500 bus, and by golly, you'd come back to the first bus, and you'd solve it again, and the voltage would change again. And you'd go all the way through a second time, adjusting 2, 3, 4, up to 500. You'd come back, and you'd have to do it a third time. The very crude rule of thumb was that the number of iterations took approximately as many as the number of buses. So a 500 bus system, 500 iterations, yes indeed. Very slow and very unstable in that oftentimes it would not reach a solution. It would diverge. It was easy to throw the Gauss-Seidel off, and it wouldn't converge. I drew a graph down here that said this is the iteration count going out here, and if you start up here, the log of the max delta P, the Gauss-Seidel comes down very slowly. The decoupled comes down less slowly, but it's fairly it's a very fast method. Here's the Newton. It converges the most rapidly, but of course each iteration has quite a lot of work, as you have to build the whole Jacobian and then do its table of factors to get the solution. But in terms of number of iterations, the Newton will converge fastest by number of iterations, although this one is the faster. The Gauss-Seidel, again, the only advantage is that it takes just a little bit of memory. Where I have seen this still used today, doing large power flows, oftentimes power system planners will take the Gauss-Seidel, they'll run maybe 10 or 20 iterations of the Gauss-Seidel. That can be executed fairly quickly because it doesn't have any matrices to do, and then switch into the full Newton or the decoupled, because that gives it a good starting point. It's a good way to start the calculation off, rather than the Newton where you start and you may take such a big step, and the first condition on the system may not give you a good place to start from, whereas a 10 or 20 iterations of the Gauss-Seidel will. Okay. The linear or the DC power flow is just the p theta calculation from our decoupled. So we use this equation. PIK is 1 over x, the line susceptance, times the difference in the phase angles. Now this is in per unit. These two are radians, and this is in per unit. Later chapters we'll make sure that when we want this to be in megawatts, you have to put a factor of 100 times this equation. But then we say that the bus equation is the sum over all the buses connected to I times the P. This really should say IK here, bus power equation. And so it's our old friend, the B prime matrix. And to solve, we just do one matrix inversion. That's it. You solve a set of linear equations. That gives you the delta thetas. When you update the delta thetas, you're done. You're done with this solution. So it's very, very popular to use this. We'll see that it becomes very popular in security analysis, where we need very fast solutions. Being linear, I can do all kinds of things with superposition and things that I can't with an AC power flow. And it is very widely used. It's very widely used in optimal power flow as well. Transmission losses. We said way back in the intro that one of the things we have to worry about is the fact that there's transmission losses in a power system. Here's a simple power system of which this generator is hooked to the same bus as the load. The load is 500 megawatts. And these are identical generators, and we said that the losses on this line are 0.0002 times P1. Whatever value of P1 is coming in, we lose this much. And so how do we get a solution? Suppose I say, well, okay, 250 megawatts each. Now the problem is that I have losses here of 12.5 megawatts, so I won't supply 500, I'll only supply 487.5. Well, that's really not a solution, is it? So we'll put some quotes around that, because it's not a solution. I want 500 megawatts here. So I'm going to have to up the megawatt output of P1 or P2 to get 500, but I also have to take account of the losses. So where should they be supplied? Well, we can do this by writing our Lagrange function as the sum of the costs of the two generators, lambda times the load plus losses minus P1 minus P2, or this loss term looks like this. And we take the standard way of solving this, take the derivative of Lagrangian with respect to P1, and we get this derivative, or the incremental cost at P1, minus lambda times 1 minus P loss, dP1. This is called the incremental loss. You can see how terribly difficult it is to write with a mouse. So this is called the incremental loss here, and plays a big part in dispatching power systems that have losses. Similarly for bus number 2, of course this term is 0 because the loss has no term affected by P2, and then we have the sum P1 plus P2 must add up to 500, the load plus the losses. And if we solve this, it turns out that when we solve it, you'll notice that now we get a term lambda times P1. And then, we have a P1 squared in here. The equations are no longer linear. So it takes an iterative approach. You solve it once and just put the equations in there and solve it. Now, how would you solve something like this? You can use Newton's method, for example. That works. And then go back and solve it again and again until you get the solution to this. So, as I say, Newton's method, you can iterate to a solution. Well, now look at what it did. Here we had this bus out here with the losses, and here's the generator at the other end, and here's our load, and we wanted 500 over here. So it said to put 178 there and 327 there, and what is this? This is adding up to let's see, 50 something, right? So because I let this generation go back, the losses are reduced. Here's the amount of losses. So it actually puts out 506.3 generation. That's the sum of these two terms, and there's the total cost in dollars per hour. That's the minimum cost when you solve this equation. So you have to solve it, but it now becomes a nonlinear equation. Again, if there's no losses, then this term is gone and this term is gone, and it's just a quick linear set of linear equations. Okay, we're going to come back now. We're going to talk about the formality a little bit more. I'm going to say minimize the Lagrangian, where phi is the load plus losses, which are assumed to be a function of all the generation, minus the loads. Here's the cost functions. Take the derivative of L with respect to pi equal to 0 for all p, and it has to be within its min and max. And we get the following loss derivative equation and set it equal to 0. Now what I'm going to do this time is I'm going to take and I'm going to flip this thing that I'm circling here. I'm going to flip it around and multiply it times the incremental loss and say that's equal to the Lagrange multiplier. And this thing is called a penalty factor. Think of it this way. This is a factor that multiplies the incremental cost times every generator, and then they all equal a value lambda. That's the same. And this thing actually gets to be large. It means that the losses are making this generator look more expensive. So it's as if you multiply by a larger fuel cost. If this thing is less than 0, it means that this has an advantage when it comes to supplying losses. So we simply multiply the penalty factor times the incremental losses equal to lambda. You remember I said that you could take and draw the incremental cost function for each generator on a piece of graph paper. Well, these dotted lines are when you take and you multiply that df dp times the penalty factor. So here's one that goes up. Here's one that goes up. Here's one that comes down. Once you have done that, then you solve and you get this operating point right there. That's where the common lambdas are. Pardon me, over here. And you get these values for dispatching. I'm sorry, this isn't the point, it's over here. So there's the point and there's the point. The double quote ones are the solution point with penalty factors. Now the problem is that as soon as you change the dispatch, you do the calculation, and you go and you change them, then these penalty factor terms are going to have to change again. And in fact, what we're going to see at the end of this lecture is that the penalty factors actually come from the power flow. So it's an iterative process. Calculate the penalty factors, do the dispatch, go back, calculate the penalty factors again, do the dispatch again. And if you don't put it all into one calculation, you then have to do an economic dispatch, then the power flow based on that dispatch, then calculate the penalty factors, then do another economic dispatch, then do another power flow, etc. So it gets to be a little longer process. I'm going to talk about something first. I want you to understand what we call the reference bus penalty factors, and then we'll show that we can derive them directly from the power flow. Suppose we change the generation on bus I by delta pi. Then pi is equal to, the new value is the old value here plus the delta. To compensate for that increase, the reference bus drops by p ref. So the new value of the reference bus is the old value plus delta p ref. And delta p ref must equal minus delta pi. We're assuming that so if this is a positive number, then p ref would go down. There's some change in losses too. And so we're going to say that the losses change. Now if this goes up, okay, and the losses go up, though, that's going to affect how much this actually has to go down. Okay, so this equation, if you want to study the SIGNs, the signs in here, they are correct, and it allows for the fact that if the PI goes up and the losses go up, well, then this goes down by taking this difference in here. And we define the beta as the change, the negative change on P ref divided by Pi. So this quantity is positive. It's a positive number. The way I've defined it here, so that if Pi goes up, then this goes down. But I'm putting a minus sign here. It's considered a positive number, and we just substitute this into the equation. And then we say beta is equal to, and we come out with our old friend, the penalty factor. Well, it's 1 over the penalty factor, 1 minus the incremental loss. Now, let's do economic dispatch with these reference bus penalty factors. So if I'm looking at all the production cost and I say I'm going to change PI and I'm going to change P ref, what's the change in production cost? Well, to a first approximation, we take the derivative of Fi with Pi times delta Pi, the derivative of F with respect to P ref times delta P ref, and we add them up. Now we know that this one is going to go negative if this one is positive, okay? But that tells us what the total change in production cost is. And it turns out then that the delta P ref from our definition before is minus beta times delta Pi. So I can substitute that into this equation, and I get this. And so it says the production cost then would be 0, meaning you're at the optimum. When are we at the optimum? Well, I can take a slight increase on delta Pi and reduce delta P ref, and the production cost doesn't change. I've reached that that optimum, that sweet spot where I'm at the minimum. Well, then this comes out to be 1 over beta times dfi dpi is equal to the reference bus cost. All right. Well, if that's the case, then I can always calculate these, and now I have this penalty factor out here is 1 over beta sub I. We get those beta sub i's. They are actually, remember, the change in the P-ref with respect to delta P1, and we build a vector of all those quantities, and notice that I've interspersed it with the d-ref dq, because I'm writing this for the whole AC power flow. This is our Newton. That's the Newton. That's the Newton power flow. I'll just say PF. J matrix, but it's transposed, and notice that it's then inverted. We transpose and invert it. This are terms that you normally don't build into the Jacobian, and they are the change in the reference bus with respect to a change at phase angle on bus 1, a change in voltage at bus 1, change in phase angle bus 2, and so forth. In the text, you can go through a little deeper explanation of how you come up with this. But this produces these terms here, the dp ref dp2. Those are the negative of this beta term that we're looking for. So we could take the power flow. Once we've solved the power flow, we calculate these terms multiplied by J transpose inverse, and we get these terms. We put them back into our economic dispatch. We do the economic dispatch. We come back, solve the power flow to equal that dispatch, get new values, and iterate to a solution. Thank you very much.